In this video, we're going to discuss the relationship between activity series and electrochemistry. And there are two ways that we can look at these kinds of problems. We can look at it qualitatively, meaning that there are no calculations to be done, and we can look at it quantitatively, meaning we are going to do some calculations. And the level that you pick probably depends on the class that you're taking. A Chemistry 1 student is probably going to do this qualitatively, whereas a Chem 2 student would probably do it quantitatively. However, if you're taking a multiple choice test question and you don't have any means of doing a calculation, you could always approach this qualitatively and still answer the question. So let's go through a sample problem. We're going to do it both qualitatively, meaning no calculations, and quantitatively, meaning yes calculations. So let's pretend we take a strip of magnesium metal, we put it in a solution containing Ag+. Okay, so the Ag+ is dissolved in some water, and we stick a strip of magnesium metal into this solution. And we want to know, is anything going to happen? So if a reaction occurs, this is what it's going to be. The solid magnesium from our strip is going to become magnesium ion and 2 electrons. Losing electrons is oxidation, right? LEO, lose electrons, oxidation. And then where are those electrons going to go? Those 2 electrons are going to be gained by 2 silver ions to become 2 silver metals. So gain electrons, reduction. So if you remember the mnemonic device, LEO says GER, LEO, lose electrons, oxidation, gain electrons, reduction. LEO, GER. So reduction is gain, oxidation is loss. So this is the reaction that would occur if one's going to take place. So we need to figure out, is something going to happen, yes or no? So the rule here is we look at our standard reduction potentials. And if the substance being reduced, in other words, if this substance, if Ag+, is higher up on the table, in other words, if it has a larger, more positive E value than the substance being oxidized, namely the Mg2+, well, remember Mg, but this is a reduction table, so it'll be listed as Mg2+. If the substance being reduced is higher up than the substance being oxidized, then the reaction will occur. So let's look at our table. This is just from the textbook here. Every textbook's probably got one of these. If you don't have one in your textbook, you can just look it up on the internet. Okay, so there's Ag+. Now remember, these are reductions. Everything is written as a reduction. So even if it's an oxidation, you got to find it as a reduction. But this is the reduction, right? And its value is 0.8. And then here is the oxidation. Now remember, it's written as a reduction. Its value is negative 2.37. Okay, so I wrote them out on my paper here just for simplicity. If the substance being reduced has a larger, more positive value than the substance being oxidized, then the reaction will occur. So what's being reduced? Right here, we've got Ag+, larger, more positive. Magnesium does not like to be reduced, right? It likes to be oxidized. So because this value is so negative, yes, this would occur. That's the way we would answer this qualitatively without doing any calculations. Now there's another way that you can do this just by looking at an activity series. This is probably the way a Chem 2 student would do this qualitatively, because most Chem 1 students don't deal in standard reduction potentials. And there's another way that we can answer this problem. If you flip back in our textbook, this textbook's about 10 years old, but the information's all the same. If you look at the activity series, your textbook has something similar to this. Now, the one note that I want to make is that if you're going to look at an activity series from your textbook, instead of looking at standard reduction potentials, the rule is reversed. So if we're asking ourselves the same question, will magnesium metal reduce silver 1? Same question as what we just asked. Now we need to look backwards. If it's higher up, the substance being oxidized is higher up. That's our rule, okay? So when you're looking at the standard reduction potentials, notice we looked for Ag+, the substance being reduced, to be higher. If we're looking at a activity series, it's the other way around. Okay, so it just depends on which one you're looking at. If you're looking at an activity series, which is literally just a list as reducing agents, versus if you're looking at standard reduction potentials. Just the rule's different based on which method you're looking at. Are you looking at a list of standard reduction potentials, or are you looking at an activity series? Okay, so that's the qualitative treatment. Now, if we're going to do this quantitatively, i.e. doing calculations. We have to calculate delta G. So same question. You have a piece of magnesium metal. You place it into a solution containing Ag+. Is anything going to happen? So we have to answer it quantitatively by doing some calculations. We're going to calculate Gibbs free energy. And technically we could answer this just by calculating E cell, but let's go ahead and take it all away, calculate delta G. So if delta G is a positive value, then it's non-spontaneous. In other words, this reaction won't occur without outside interference, some sort of electrical current, in other words. Or if delta G is negative, that means it's spontaneous. The reaction will occur on its own. We don't have to heat it or add electricity or anything. It'll happen on its own. So delta G is calculated by the following formula. Negative, don't forget the negative sign, N, where N stands for the number of moles of electrons transferred. F is Faraday's constant. And E cell we calculate as cathode minus anode. Okay, so if a reaction occurs, this is what it would be. I just rewrote the problem. Magnesium metal is going to become magnesium ion, and its E cell value, again, I just took it straight from our standard reduction potential value, which is negative 2.37 volts. And Ag plus is gaining 1 electron to become Ag, but to balance it, I put the 2 there, multiplied the bottom reaction by 2. However, just a reminder, when you multiply a reaction by 2 in electrochemistry, you do not do it to the E value. When you're doing a calculation like we did in Chem 1, where we're doing Hess's law, if we multiplied by 2, we'd multiply the heat of reaction by 2, but that's not the case in electrochemistry, because electrochemistry is not dependent on the number of times the reaction occurs. That's why we wouldn't multiply by 2, like you do in Hess's law calculations. So how did I know which one was the cathode and which one was the anode? Remember, red cat. Whatever reduction occurs, that is occurring at the cathode, red cat. So this is the reduction right here, so that must be occurring at the cathode. Okay, red cat. Whatever reduction occurs, it's occurring at the cathode. And again, that 0.8 just comes from my standard reduction potential. Now your textbook might give different numbers of sig figs on these values, so don't freak out if yours says 0.79 instead of 0.8. Okay, it's just dependent on the number of sig figs that your textbook publisher decided to go with. So E cell is cathode minus anode, so 0.8 minus a negative 2.37. So that gives us a positive 3.17 volts. So technically we could answer the question by just doing E cell, right? Because if we calculate E cell and we get a positive value, a positive E cell is spontaneous. However, we want to be extra confident, so we go back to our delta G calculation here. Okay, so if delta G is negative and E cell is positive, then we know we've got a spontaneous condition. So now let's just finish the problem by calculating delta G. Delta G is calculated by negative N. N is number of moles of electrons transferred, so that's this value right here, times Faraday's constant, which is 96,485 coulombs per mole electron. So that's where my electrons cancel out. And a volt is the same thing as a joule per coulomb. So coulombs cancel. So that's how I end up with units of joules. Okay, I always like to show where the units come from, because sometimes students get confused about the units and they go, how do I get units of joules here when I was dealing in volts? Well, a volt is the same thing as a joule per coulomb. Coulombs cancel, moles cancel, and I'm left with joules. So this is what I get when I punch it into my calculator. Rounding my answer to 3 sig figs gives me negative 612,000 joules, or negative 162 kilojoules. Delta G is a large negative number, so that relates to spontaneous. E cell was a positive value, so that relates to spontaneous. So based on all that information, we would conclude, yes, a reaction is going to occur. You will see solid silver forming on the magnesium strip. So no matter which way you do it, either quantitatively or qualitatively, you get the same answer. So I hope this helps you in dealing with the activity series and how it relates to electrochemistry.